geospatial systems. And we spoke about remote sensing, GIS, and programming 3D. Okay, so let's continue from there. We need to do this. Okay, so this I think I don't have to go through. Remote sensing I already explained, right? What is remote sensing? But the point here that what you should pay attention to is that so you have the satellite system, okay, which is orbiting in the orbit, obviously. Then you have the solar energy that is coming and passing through the atmosphere. Obviously, when the energy passes through the atmosphere, some of the energy gets lost, right? Some of them will be scattered. That's how you see the colors. The sunlight is different color, the sunset is different color. The reason being, the ability of the color to be scattered, right? So the blue light gets scattered more, right? That's why you see the blue star, right? So that is what you call the Rayleigh scattering. Remember, recall back now in your physics that you have learned about Rayleigh scattering. Okay. So when I ask question to MTech students, sometimes they say it's because of the reflection from the water bodies. That's why the sky is blue. Okay, so that's not the case. Okay? So whatever energy now, after passing through the atmosphere, it comes and then interacts with the object. And you have different types of objects. And each object obviously has its own chemical composition. For example, if you look at the rock types, okay, you have granitic rocks, you have metamorphic rocks, you have sedimentary rocks, and blah, 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 right? And every rock has its own minerals, and the mineral has got its distinct properties. How they interact with this electromagnetic radiations. Okay? So now the point is, we need to understand how do they react with these objects. Is now being reflected back. That is what we are interested in. We are not interested in what is being transmitted, because obviously when energy interacts with any object, some of the energy will be reflected, some of the energy will be transmitted. We are plugged into it, right? So we are interested in how much of energy that is being reflected back. So now using these systems here, see I can't use that because there is yeah. So using these scanners here, that records actually that amount of energy that is being reflected back. But again, it has to again pass through the atmosphere. Some of the energy will be again lost. So you are not getting 100% for sure, right? But whatever is being now emitted back, now I use the word emitted back or reflected back, that is what actually we capture it. They are normally being recorded in terms of digits, 0, 1. Now we decode those digits and then we convert into images, right? How do we convert them? So this 0, 1, so obviously you might have heard about 1 bit, 2 bit, right? What is that? You know how the information that you are projecting on the computer or on the projector, it has got different bits, right? You have 3 inputs. There is a red channel, there is a blue channel, there is a RBG, red, blue and green. Why this RBG? What is that primary color and why do we color that as primary color? Yes, so morning I spoke about it, right? Among the electromagnetic spectrum that we have this much, only this tiny amount of width through which we can be able to see through, and that is called RGB. And I mentioned about also the wavelength 0.3 to 0.7 micrometer, right? So that is why you have these 3 primary colors. Okay? All other colors actually you can generate from the mix and match and all those things also you can get, right? So 0, basically it is 256, what do you call, the gray level values that we have. That's what we call the gray level values. So 256 means 0 to 255, right? Because 0 is counted as 1, so 255. So depending on that, you have different types of bits. So then based on that, they classify the image whether what is the radiometric resolution of the image. I think that you will be learning about in the remote sensing class by Professor Pasupuleti, right? Professor Srinivas. All right. So this is what essentially I have mentioned. Now you can see in this particular figure, you have different kind of features that is existing on the surface of the earth. You see the land is part, they interact totally differently. Then again you have different types of vegetations. You have forest, different types of forest, coniferous forest, and there are different types of forest, right? Then you have water bodies, then there is in geology, different types of soils. Then obviously we are also interested in the elevation model of the earth. That is what you call digital elevation model. You know about digital elevation model, DEM? Okay, good. Then, so pretty much all the processes that is happening on the earth, to certain extent, to certain degree, we can be able to monitor them globally. Okay, we have the ability to monitor the earth every 10 minutes. There is a new generation Earth observation satellite, geosynchronous Earth observation satellite by Japan every 10 minutes. Man, how much of data that we capture? How the vegetation has been changing, okay? How the color of the vegetation, color essentially means shows the healthiness of the vegetation, isn't it? So how it has been changing, everything pretty much can be monitored. Okay, understand? So from here we can see, we can monitor our glaciers, we can monitor our volcanoes, we can monitor our land use, the way we are changing the land use. We can monitor if the sea surface temperature, the temperature has been increasing or land surface temperature is increasing. So pretty much all these SDGs that I mentioned, all these directors that can be, all the indicators that we are talking about, it all can be monitored. Clear? Okay, good. So now GIS. See, I have just one slide of remote sensing. And one slide. If needed, if you want, I can give you much more elaborative lecture later on, if you need. Okay. So now GIS is a system. It's a system where you create data. Okay. It's a database management system. And beyond that, because it allows you also to query the data, to analyze the data, to manipulate the data, to massage the data, right? To cleanse the data, to model the data, and to create the simulations. So it is not just about creating a map. Many people think that GIS is just essentially used for the mapping. No. More than the map. Okay? It's not a drawing tool. It's a mathematical, like a platform where you can do a lot of analysis. Okay? So the functionalities of GIS goes beyond whatever I mentioned here, like capturing data, storing data, querying data, analyze, displaying. You can do 2.5D modeling. You can do these days also three-dimensional modeling as well, like the miners they use. Then even site suitability assessment, right? If you want to, let's say, build a new highway, okay, from A to B, then what would be the most convenient way of building the highway without damaging the ecology, right? Otherwise, you can say that, okay, this is the shortest distance, we just build it. But that's not the case. We are interested that the environmental impact assessment should be properly done. Okay? Then, the beauty of GIS is this. All kind of data, they all essentially being captured in three ways. Okay? One is point, one is line, another one is polygon. So any information that you see outside in the real world, they all can be captured through either point, line, or polygon. Okay? Now, I'll give you a simple example. You open the Google Earth. Okay? You launch your Google Earth on your computer. Now you type IIT Dhanbad. What do you see first? Earth coming, slowly now zooming in, going in. So hold on now. You see at that time, India looks like what? A small polygon. Yes. That means as if you are looking from Mars. Right? Imagine now. Right? When you type, so obviously you see that, then like that. Then you see that Earth is, now India, the shape of the Indian subcontinent shows like that. Slowly zooming in, zooming in, zooming in, zooming in. Dhanbad is point. Right? Slowly zoom in, zoom in, zoom in, then it comes to the campus. What I wanted to tell you, what you experience there is basically something to do with the scale. Right? In what scale you are representing the data, actual data, that is what essentially you are looking at. That means the same location or area can be presented in 1 million scale, or it can be just 1 million scale means it's a very rough scale, right? That means it can be just a point. Like if I would like to say, map Earth in your universe. Can't even locate, can't even point. The blue dot I was looking at last week, the Hubble telescope, you know? Yes. One last time when it was going beyond at the edge of our Milky Way. Okay? That's what they have estimated about. I don't know how many billion, 250 billion light years or something like that. So they wanted actually just to pinpoint towards our Milky Way, towards our solar system, just to see that how Earth looks like. And if amazingly if you see that figure, that photograph that has been taken by the Hubble telescope, just small tiny fractions of the blue. That's all. Marvelous. That is something to do with scale. Now if I would say, or I would ask that I would not want actually map of Dhanbad in 1000 scale. Then you have to draw the entire plan, right? So that is what the data is being captured, right? But essentially we try to capture the data in a very high resolution. High resolution means as detailed as possible. Now think of it. If you have a 5 megapixel camera, you take an image, your photograph. Okay? Now that is the maximum that you are taking, right? That means the 5 megapixel is my 5 megapixel. 1 pixel size is 5 megapixel. What is the size of the, let's say given size, X size, right? Now you have actually all these digital images processing, the image processing softwares. Yeah, thank you. Image processing softwares, right? Now if I ask you that convert into 20 megapixels, digitally you can be able to do that. Okay? But in a real life scenario, it's rubbish. Right or wrong? It will be pixelated. But if you take the original photograph in 20 megapixel, now I would want to reduce down to 5 megapixel. That's all right. Are you understand my point? Yes. Similarly, how this scale concept comes in. Many people don't understand. They think that, okay, GIS, we can just take the data, we can manipulate the data in GIS. No, you have to understand the scale. Harmonize the data so that all data makes sense. Okay? So, point data. What are the point data? Poles, electric poles. Then, what else? You can think of it. Any point data. School can be a polygon. I would capture school as a polygon. Campus is a polygon. In the campus also, every buildings are polygons. Water tank is a point. Okay? Street junctions, lights, blah, blah, blah. Trees. Right? Those are point data. So that means those data should be captured in a vector format. I'm talking about vector and raster, there are two different things. And they can be easily converted to each other. But vector to raster is better. Raster to vector is not that good. Because it generalizes. Right? So one is the point. The next is the polygon. So, polyline. Line data means stream network. Right? Drainage network. Then you think of rivers and all those things goes. railway lines, correct. Then you have road networks. Then you have that's the polygon. No, I will tell you that, but that's a polygon because country is not open-ended, right? Right? Country is bounded, correct? So then, okay, many other examples. Think of it. Now comes the polygon. Polygon is basically parcel, land parcel. Your farmlands, your campus, your building footprints, ponds, rivers. But now, the point is, depending on what scale that you are presenting the data can be presented either is polyline or polygon. Okay? But essentially, all data captured as points. Because you start as a point, to draw a line, you need another point. Then you draw a line, you connect it to them. Then you draw another point, then you draw another point, you connect them, come back to the first point, make it polygon. Right? So essentially it is about the points. And every point you should have a coordinates. That's what, otherwise it's not the spatial data. Correct? Am I motivating you enough actually to understand the concept of it? Yeah? Okay. So now you have X and Y. Now there is another dimension to it as well. If there is a height difference, like the Earth's surface, we have height, building, it's a height, right? But the new generation surveying equipments, like satellite data also, we have the way actually to also generate the height from two images if they overlap with each other by 60% using the programmatic techniques, parallax and all that. Remember in physics we have learned about it? Yeah, like how actually the way also we visualize everything, two dimension. It's not parallax, it's physics, right? Okay? So essentially you have points, point and polygon, and they are all being captured as individual layers. And they have been stacked together. Finally you produce the beautiful maps, scenarios and stuff like that. Okay? So whatever you see outside is all being captured through different means, three different means. Okay? And we know there are thousands of satellites that is going around the Earth. It has already become very crowded. So space debris is becoming a big issue for us. Okay? Because every satellite that we launch, it has its lifetime. Like human being has its own lifetime. But sometimes they go beyond actually what is being designed for. Electronic items, you never know. Right? The Mangalyaan. And also the first one missed out, the moon mission, Dhanbad, right? So, sometimes it go beyond. Let's say designed for 20 years, but then it goes another 10 years. Or sometimes designed for 10 years, but it works for 5 years. Right? Electronics. Okay, so it's getting very, very crowded because every country is launching their own satellite, and there are different types of satellite. So, but we are interested only in Earth observation satellites. And also the communication satellites, because that's why you are communicating, the radio signals, right? Without that, the Wi-Fi and all these things are not going to work. Alright? So, now, how does these things work? Now let me just quickly show you this multi-band display. You know that photograph that you take with your digital camera, it has got 3 bands. Bands means 3 channels, okay? You open that actually in your Photoshop, okay? You will see that 3 bands, right? R, B, G. So what we do when we develop the sensor for the satellite, so using what portion of the electromagnetic spectrum that we are interested in, and which object are sensitive and the way they interact with that portion of the electromagnetic spectrum, we design the sensor. Okay? We may have thermal sensor if we would like to know the temperature of the object. We may design, let's say, beyond red band. That means near infrared, mid infrared, far infrared, so on. Right? That will be beyond 0.7 micrometer. Okay? Or if you are interested in, let's say, so depending on different this kind of bands, we can actually design the sensor. Okay. So if sometimes we may, depending, like we have Landsat, it has got X number of bands. Let's say we have Worldview. Worldview is a commercial satellite launched by the US, and that's pretty much expensive. Like one scene about 25 square kilometer can be $600–700. It's very expensive. And we have our own satellite called IRS, okay, Indian Remote Sensing satellite. So we have a series of satellites, and they are all being designed for specific purpose. Okay, so they exploit actually the different bands of the electromagnetic spectrum, right? So now imagine we have 8 bands. Okay, let's say RGB, and then we have beyond red band, mid, hard, and blah blah blah. Okay, so but ultimately, when you would like to display on your computer, you can only display 3 at any given time, right? And that is RGB. The inputs would be RGB. So it's up to us what input that you are giving and assigning the RGB of the computer. That is what you would like to see on your screen. So that is what you call multi-band false color computation. Okay? Huh? Understand? So if your original image, okay, has got 10 bands, among them there is also RGB, but if you are presenting the RGB and assigning them RGB to the computer, that is what you call true color composites. True color composites are not that useful for us to derive a lot of information. So that's why we try to play and trial and error kind of thing. We come up with this false color composite so that some informations which may not be visible or derivable through true color composite can be derived through false color.
So what is the reason for this limitation? 3 bands?
Because different bands are unlimited. That's how the
No, RGB, no matter how many bands we have, we can only show 3 bands.
Yeah.
So what is the reason for this limitation?
That's how actually we are human beings, we can be able to see through 3.
Oh, that is the reason. We can see only these 3 bands.
That's the limitation. Are you getting me? I try to explain in a very so that everyone can be able to understand. I assume that not all of you know remote sensing. Okay, understood? So this is what it is. So this is a good example. Okay, band X assigned to R band, band Y assigned to G, band G assigned to B. So all these called color composites. Okay, and all these bands can be stretched. Digital image processing, that means the histogram equalizer, all those things can be done. Stretching, like how you manipulate your photograph using the Photoshop. Right or no? You touch up, take the thing, touch up, then you make it sharpen. So these are called image processing. Okay? Now, this is the example. Now pay attention to it. You have 7 bands here. Now, the 3 to 1 is assigned. This is called, see, red, green, blue. That is, see the difference. Oh. See, now look at it. See, if I put red 422, that means band 4, green and blue, this is what it looks like. But if I change, because I have made like, okay, we'll go back. 3 to 1. See 3 to 1, band 3, band 2, band 1. That is, see the information actually of the same image, but it looks. Okay? Now, if I change 4, 2, 2, that means band 4, red, band 2 actually is green, and this is blue. You see the information is totally changed. Right? So why? Because I mentioned different objects, they interact with this electromagnetic spectrum at different wavelength differently. So we would like to exploit those and try to learn. It is very, very useful, especially when you want to do the visual interpretation. Okay? So when you interpret things, one is for 432, sir. So that means, so imagine, so certain information which is not visible in certain band combinations, they will be more enhanced or differently to appear actually in a different band combination. Okay? Are you understanding?
Yes.
Now see here, this is the true and false color composite. R is red band, G green band, D blue band, Landsat 321. Okay? The same image, but it looks C on the left hand side. But when it is 742, that means short wave infrared, near infrared, and the green, you see 742. So the forest, in a true sense, looks like this, isn't it? If you want actually to extract information about the forest and stuff, you would want this color combination, right?
Yes.
Okay? Very well, cold? Feeling cold? Okay. So, got me? Okay? Now, this particular slide shows different types of geospatial data captured by different systems. First one is captured by UAV, unmanned aerial vehicle, or this by this drone. Okay? And this can be captured at a very high resolution. Can go about 15 centimeter pixel size. 10, 15 centimeter. Okay? But again, depends on what height that you are capturing the data. Always looks like that. I mean, this is how far you go, the wider you see, but the quality of the information you have to compromise. Right? So I use the word spatial resolution. Spatial resolution means what is the width of the pixel that represents the real world scenario. Okay? That is what we call spatial resolution. The radiometric resolution is how many bands are there. Okay? And so on. So you see, that is one. Second is MLS is called mobile laser scanner. So that means this is data captured by me. So you are driving the vehicle and the laser scanner is being mounted actually on the top of the car. Then it is rotating 360 degrees. As you are driving around on the highway at the speed of 50 km per hour, 60 km per hour, same time we are capturing actually millions of points, point clouds of the surrounding area. Wonderful. Then you finish driving about 10 kilometers, come, unload, you then transfer the data and see billions of point clouds. And with the software you can just process and you can make the 3-dimensional view of that. Okay? So terrestrial laser scanner, we have that. So if you just put it here, within 15 minutes I can capture it all in a pretty good resolution. The way you are sitting, everything will be captured as it is. Okay? So then, now you can imagine the power of this data. Because a lot of information that I can extract from this, for example, highway geometry, the quality of the pavement, everything pretty much you can be able to derive. How many of you are civil engineers? So a lot of analysis can be done. Okay? Then obviously Google Maps. Don't understand the power of Google Maps. Yes, there is a famous word there. Dialogue, sorry. Common map. Here there is, do not actually underestimate the power of the Google Map on Google Earth Engine. There is so much of data that is there, and that's for free. And it's for free, and you can build actually plugins and then there are a lot of codes that is being already available. You can just tweak and turn, and then you can try to do whatever is for your own applications. Okay. Then that is called LiDAR. I'm just giving you some examples, but obviously there are plenty of other types of equipments and systems through which you can be able to capture the data as well. So this is LiDAR. LiDAR is light detection and ranging. So it's laser scanning data. Okay, very, very powerful because this is an active remote sensing. So LiDAR and the first one you see the synthetic aperture radar, those are active remote sensing. That means regardless whether the sun is out there or not, regardless whether it's a day or night, regardless whether it's raining or not, you still can be able to capture the data 365 days, day and night. That is why the longer wavelength that you goes in, longer wavelength means what? Okay? Regarding that, I would ask you a question. In the traffic signal, right? Why red color is used to stop the car? Right? So long wavelength means you can be able to see. So our eyes can be able to detect, I can see that. So all physics is not just, because some people think that it's a color of blood. Okay? So radar waves, they are very long wave, but the frequency is very low. No, sorry, vice versa. The radio signals are long wavelengths and frequency is low. Okay? So the radar, basically also they have different combo, like H and V, horizontal and vertical polarization and so on. Okay? It's a different, so radars mostly you see the black and white. Okay, you can see that they are not very pretty images, but it provides a lot of useful information. Especially radar is very, very sensitive to the water bodies. Okay, so if you want to analyze any target in the ocean, for example, ship detection, radar is the best. And you know how it was discovered? The application of the radar for ship detection. Yes, this is second. You know the Hudson River in US? So what they are doing, these two scientists, they are transmitting signals. Radio waves they are transmitting. Okay, both banks of the river. Then suddenly they didn't know that the applicability of this kind of signals for any particular application. No one knew about that. Then suddenly they realized the signal got lost. Okay? Then they found out why it lost, why it lost. Found out that a ship was passing. Then they were, whoa, maybe we can apply it for ship detection. Eureka. So all the discoveries that has happened in science, mostly because of this. Yeah. You don't plan. You want to discover something else, but you end up discovering something else. Oil was discovered like that, right? Petroleum was discovered like that. So that is why I always say, idea good or bad, always is an idea. Okay? And the ideas always being ridiculed by the people. Unless until it is being proven and accepted by the science. Don't say scientists who everyone calls scientists themselves. It's about the community. Right? That's why the first paper, the theory of relativity paper of Einstein was rejected 3 times. So imagine if you don't have published that. You would have thought, no, everyone is criticizing this rubbish. What would have happened? Imagine if Galileo's idea was not finally, he was prosecuted, right? When he said that no, Earth is not the center, it is the sun who is the center of our universe, right? Our solar system. He was ridiculed. And that was what, 300 years ago, 400 years ago. Okay? So we say in science we have progressed this, but it's not too much. Not really. Okay? So those kind of data sets are very useful for soil analysis. Okay? And since it is very sensitive to the water body, so a lot of information also can be captured that is related to those. Okay? Moisture, this and that and all that. Okay? Now, let's look at the applications. Now, having known that what these technologies are, now we can pretty much visualize how they can be utilized in different applications. I'll list it down some. Agriculture, we'll go through one by one. Agriculture, water resources, those who are working on water resources, rural development, those who are working in city building, city planning, blah, blah, blah. Natural resources management, mining, forest, everything natural resources, okay? Disaster management, landslide, earthquakes, tsunamis, coastal erosion, floods, what, name it, okay? Forestry and ecology, geosciences, like what? Producing mineral map, producing structural map, producing lithological map, okay? Those kind of map, I say map, but these are information, right? Urban and infrastructure, information services. Imagine, our cities are rapidly changing, right? Because the population is expanding, cities are expanding. You visit actually a city after a year, you will see that the facade of the city has changed. So much of development that has been happening, right? So gone are the days when we used to do the traditional way of mapping and collecting the data and updating the maps. Go on, you can't keep it up. And the amount of human resources that you need to do that, it's mind-blowing. Okay? So what do we do now? We engage the satellite-based information and we automatically update the maps. That means we extract the information from the satellite, the new developments happening, there is also we extract, then you keep on adding those pieces of layers of information to the existing body of information. And we have already automatized the process. That is where the fear comes in, people losing jobs, but it is inevitable. I will give you a simple example. Like when we drive here in India, obviously we have toll rates, right? So there was a time when, imagine 5 years ago, there was someone who was collecting the cash, right? Collecting the cash, and that was a job for someone, right? Collecting the cash, you take the money, give the money, then you drive, right? So essentially that was a job. Now that is gone. We have automatized it, but it's not enough because in Australia we don't have anyone there, and we don't have any gate there. You drive through 120. It will capture automatically. No way it will miss. And doesn't matter also if you have that card. You know what you call the sticker? Doesn't matter because the government has your car number. 110 km per hour, you are driving the car. It captures the data. That's it. So that is the fear, because when you do the automation of the automatize the process, obviously populated countries you lose jobs, but in developed countries we need to do that because we are lack of people. In Australia, whatever is being done by a human being, that would cost more than whatever is being done by a machine, because people are less, right? But here we need a job, right? So that is the fear. The more you automatize, and how this automation happens, obviously using all these ICT tools, techniques and all that, right? Now you go to parking space. any new malls, right? They don't have the who gates anymore. Do they? I don't know. I mean, here, I don't know. And here they have, I mean, they read it, your number, and they calculate actually how many hours that you have stayed, and then you just go to pay. That's it. Right? In Australia, when you pour petrol, no one is there. The entire petrol station, there is one person sitting inside. And he has to also manage the coffee, he has to also manage the, if you are going inside to pay, but you go and pour first. Imagine if you do that here. The petrol station will go bankrupt in a day. People will come, go and go. Right? So there you go, pay, there you go, pour the petrol first, and then you go and pay. Telling you, this is the truth. Okay, so automations are happening. Okay, and then that is what we have to inherit. But to what scale that we are going to do, so to balance between the resources that we have and also how many jobs that we are going to compromise. Okay, but you can't lag behind. You can't say that no, we are not going to accept it. We will just still sitting down there and collect the tolls. Then there will be huge traffic. You know, still there is traffic jam at the toll, but there we don't have. There's no thing. There's just actually, you know, there is a bar like that. Every lane has got a sensor there. You just drive through. There's no need to actually even reduce your speed. That's it. It's been cut. Okay. In 5 years' time, also would happen here. Trust me. 5 or 10 years' time. How much you register also, you can't. That's the way forward. Okay. So that is why the skill development is very important. You know? So someone just now, the media guy was asking, how would you please comment on the new education policy? It's out of the syllabus, okay? And compare that how actually the education in Australia. Significant difference. The difference is that because, especially in the school, they allow a child to pick things that is based on his or her interest. Until the age of 7, the kids learn nothing. Just play, do things that actually excites the child. यहाँ तो बच्चा पैदा हुए कैसे माँ बाप सोच लेते हैं इंजीनियरिंग करना है, डॉक्टर बनना है, बेचारा पैदा भी नहीं हुआ. Right? Imagine how much of pressure. Imagine you do so well in all these subjects, you just fail one subject and everyone criticizes and you fail. Right? So one fail doesn't actually make you a lesser person. And that's not the right instrument to judge a person's ability. Right? That was the flaw in the education system. Education is not just getting a degree. Education is not just getting a certificate. Education is getting skill. Think. Apply. Critical thinking. That's all education. Right? You know, you might have actually a certificate from IITs, but if you're good for nothing in terms of thinking and problem solving, what's the point? If someone is a school dropout, and most of the billionaires are school dropout anyway. Right? So it's proven then. Your director is going to kill me. So, meaning to say that is the difference. So, child has the choice of picking the subjects that he or she wants to. You can select law. You can still select actually computational subjects. You can select law. You can select engineering. Up to you what you want. You figure it out what you want. In school, no one would know how many you score, how many marks you scored. No display of the ranking of the students in the class. That's a very negative mindset. what happens is that, why do you do that? Imagine the person who is highly competitive, good, studious guy, now was looking for number 1 rank, now for some reason has got rank 2. And why you want to display that? For what? For whom? So what they would do rather, they would actually have a one-to-one conversation with the teacher. These are the areas that you should improve, and these are the areas you are excellent. That is the motivation. Okay? So, and everything changing. There was a time IT was booming so much. Now machine learning, everyone talks about machine learning. My nephew finished his year 12, machine learning. Everyone machine learning. But once that will be saturated, then what you will do? So follow what you are good at. That means you got to figure it out what you are good at. And science says anything that you practice continuously for 10 years, you will be remain as the best in that field, regardless the kind of skill set that you already had. You just practice, still can be the best in that. No? So that's why judging that, okay, one subject you fell, miserable, and then finished, okay, it's done, it's practice. Okay, so automation is a must. There is no other way that we can do it. Now let's go through one by one. Okay, very quickly. Let's look at what are the applications that we can think of possibly in different applications. So agriculture. Who are working in agricultural background? Who is having agricultural background? Okay. So what do you think about agriculture? How we can utilize this information for agriculture?
So mapping of the agricultural land.
Yes.
Boundaries.
Correct. But those are basic things.
Network system.
But think about
Discharge calculation.
think about how your technology can deliver and improve the quality of life of the farmers. That's what SDG, Sustainable Development Goals, right?
Sir, crop growth monitoring.
Or disease, early detection of the disease is the crops. Okay?
Yes.
So you see, now you guys are experts. You're thinking. That's important. Then what else you could think of?
How much water needed?
Yes, precision farming. Precision farming. So that is the whole technology is called precision farming. That means how much water that you would need actually to utilize for the farming, and also how much of pesticides, because the traditional way of farming actually they use too much of pesticides. Sometimes not knowing how much they are damaging.
Yes, sir.
You know, see, soil is life. You know, although we have so much of land, but the soil, the top soil where actually the crops are being generated, that is very less, and they are all getting washed away through the sedimentation process and through so all this weathering, erosion process and so on, right? So we need to protect, because that is essentially, can you automatize everything and then you don't need to eat? Right? No, we do everything automation. We don't want to eat. That's the basic things we still need, right? Sustainable development goals, right? So drought management, drought monitoring. Okay, I have 2 PhD students who finished. So like early detection of the drought, and then it's not just detection of the drought, but at the end how you try to inform those decisions actually and your findings to the farmers. Okay, so that they can take the mitigation or mitigating measures. That is crucial. Otherwise, your information is just a piece of information. It's not impacting in a real life scenario. Getting it?
Climate smart agriculture.
Hmm?
Climate smart agriculture on the basis of drought and floods.
Yes. So if you search drought and search my name, you will see many papers, many articles. And they are all latest tools and techniques, new models, new methods we introduce.
only flash accessibility or does it only like
Yeah, again, all applications. But I'm not trained in everything, right? But you got to think, can I, that what I have learned this, can I use here? Then go to learn a little bit more about that and try to think. Keep on pushing the boundary. Okay. So drought, agricultural drought, because there are different types of drought, right? So agricultural drought is something also. There is another drought what we call flash drought. That means drought within drought. So like Australia is right now is going through the millennium drought. That means 100 years it's going through the drought. Okay? But within that, you have sometimes very intense drought comes in for a week or two, or a few days, and goes on. Now my point is, can I detect, because that is going to do the damage for the farmers, right? And then, what are the variables that you would like to take? Now think, in order for us to detect, what are the variables that you are going to capture first, or data that you are going to capture first? Soil conditions, soil moisture, plant conditions, phenological cycle of the plant. You need to understand that. Otherwise, what is supposed to be, let's say, because different phase cycle, phenological cycle of the plant is going to be different, right? So all those processes you need to understand. You can't put everything in one box. Not everything can be applied in one go. You need to understand the mechanism separately. Okay? See, crop insurance. There's another PhD student developing actually weather insurance model. You check. Last week there is a new paper published on this topic. Something new. Weather insurance model. That means we want to protect the farmers. And can we develop a model which allow them, if there is any change actually in the weather, okay, so can they be protected? Insurance. So again, how I integrate GIS and the spatial and machine learning models into that. Okay. Then identifying scope of crop intensifications. Also, bioenergy, include field instrumentation, blah blah blah. The list continues.
Sir, I have a question, sir. Which meteorological data do you use?
So many types of data we use. In
In India, like we use the IMD based data, but there are like 2 or 3 stations in a district, so it is very uneven result. Grid data is basically used for
grid
IMD,
data.
but it is not
What
actual.
you see, especially IIT Gandhinagar guys, they are doing good work in out, especially Biswajeet. They are working together with some US guys and all that. But now I'm also working with IIT Jaipur and IIT Kharagpur. So we are also going to rely on these phenocams. So we have access to some phenocams and all that. So data is not an issue. Drop me an email if you are having some concern about data. Don't care about the data. Right now, as I mentioned, 20 years ago, if you would have told me about data, there is an issue. Okay. But now, what? So much of data is available. Your machine is not enough actually to process it. We have supercomputers. Okay? So, agricultural, think of it. Okay? There are so many applications we can think. I had a PhD student 7-8 years ago. He completed on disease detection. Okay? In oil palm. So what we did basically, we created a nursery for it. We, from the very early stage of the oil palm, as it was developing, we injected actually the virus. We wanted to study that, how actually the virus is reacting with the plant. Then we started collecting this data with the handheld cameras and all that. Then tried to analyze the electromagnetic spectrum and the spectral signature. Everything can be done. Okay? Water resources applications. What are the, think of, don't look at slides, just throw some
Flow informing, groundwater, flash flooding,
yes,
liquid detection,
yes,
glacial outbursts, groundwater mapping.
glacial lake outburst, but that can be under disaster. You said glacial lake campus.
Groundwater map.
Groundwater contamination.
Water quality.
Seawater intrusion. Okay. Then
So mostly used in like HHMS, ACRAS, flood modeling, groundwater modeling.
many. I've developed many models. Okay. I've developed many ensemble models. Both hydrological, hydrodynamic combined with HV machine learning based model. And stuff. Okay. So models are plenty. Okay. And my job is not to develop a new mathematical equation. There are mathematicians who are doing that. They are good at doing that. My job is to try to see that what they have identified and how I can think of using in my area. Okay, so that I can improve the existing predictive systems. Okay. So there are so many here: cloud warning system, evapotranspiration, glacial lakes, snow melt runoff, hydrological modeling, irrigation management, hydrological drought. So there you have agricultural drought, you have hydrological drought, then you have meteorological drought also, a different type of droughts, and so on. Okay. We will go through this 2 weeks program. Some examples also from A to Z. That means we take the data, maybe we will look for forest fire, depending on how much time we have, or maybe we do landslide, or maybe flood. I don't know whether I have got the data for flood or not. Okay, but I'll show you from point A to point end point. So at least you should learn how you can do the modeling process. Okay, but first we need to understand the whole concept first.
So there is a break.
Okay, right?
It was from 4 to 4:30. Skipped it.
आज के लिए समाप्ति.
Yes.
Okay, good. मेरा तो एक ही अभी है.
So we were discussing कि अभी तक तो 2 ही slide पार हुआ है.
As I mentioned earlier, it's not about me finishing. I can. I have the ability to go through 60 slides in 20 minutes. But I have also ability to go 60 minutes with 1 slide. Right? But it's all about, because you guys don't have the background. So if I don't give you the example, the context, the preamble, you get a certificate in any way. Am I monitoring who is coming, who is not? You get a certificate. If you are coming here for a certificate, not useful. But if you have come here to learn something, as I said, 40%, 50% learning also consider successful. Okay? Okay, so we will continue tomorrow.